All right, friends and neighbors, I think this is probably going to be our last stop on this aggregation tour. So far we've talked about the RFCs. We did a quick example of subnetting and then supernetting. And then we started working through this large topology with aggregation. And we were trying to break up that Class C address space and then aggregate it all back together and assign some addresses in a way that made sense. So this was the topology that we were working on. So if you got to this point and you didn't see what we did before, maybe you should go back. But we've got 9 routers, 18 networks, lots of point-to-point links. We've got networks with hosts on them, and so on and so forth. And here is where we left it, right? We broke it all up. We said, well, we've got 18 networks. It's not a power of 2. That's a bit of a bummer. We got to create 32 subnets. That means /29s everywhere. And if we assigned everything and it was the equal size space, then this is what we would do. But we also sort of recognize that if we're clever about how we assign things, at least some of the routing table entries can be summarized or aggregated together. So on R4 and R5, we can do some aggregation. And then on R3, we can do a lot of aggregation, /26s, along with the directly connected /29s. But then we said, well, this is quite wasteful. So let's see if we can adjust this a little bit to kind of reduce that wastefulness. And before we get too far, what do we mean when we say we've got wasteful addressing? What is that all about? Well, if we start with our class full network size, we got a class C that is 256 possible addresses, right? But we call that 254 usable because one of them is the .0, which is for the network ID, and then we got the broadcast address. And we don't usually assign those to hosts, and so we start with 254, 253 if you say, well, you got a router out there, but that's kind of the way that it goes. So we say that we can't use 2 of those addresses. They have a use, but we can't use them for hosts, and so we might say that those are wasted. But the efficiency that we're dealing with there, 254 possible addresses out of 256, 99.2% efficiency, still pretty good. But when we start subnetting, the percentage of wasteful addressing goes up, and so our efficiency goes down. So if we create 4 subnets, we need 4 subnet IDs and 4 broadcast addresses. So now that's 8 wasted addresses. And so we're now 248 out of 256 for 96.9%. Still not so bad, right? But what if I go to what we were doing right now, which is 32 subnets? Well, all of a sudden, we've got 64 wasted addresses, 32 subnet IDs, 32 broadcast addresses, and all of a sudden our efficiency is down to 75%. Ouch. Right? So that's getting to be a little bit painful. We took a whole chunk of our address space and we can't use it for hosts. And so we got to rethink how we do things. Those point-to-point links are one of the places that we can do some serious conservation of address space. So a very common practice is to assign /30s everywhere. Remember that if we assign /29s, we've got 8 addresses per network. But we know that on the point-to-point links, that is the links that connect routers together, we don't have any hosts. So a /30 is a very common way and very straightforward way to preserve addressing. So you go to /30s, and what ends up happening is that you only have 2 host addresses. So you put one on one router on the end, and the router on the other end gets the other IP address, and then you still got a network ID, and then you still got a broadcast address. So that works out really, really well. And that's been the standard practice for a long, long time. If you go back far enough, there's actually discussion about what to do about the point-to-point link problem. And it turns out that very early on, way back in the late 1980s, they recognized that point-to-point links, which are used all over the place, we use them in our organizational background or backbone networks, but we also use it all over the internet. A very wasteful portion of the internet as a whole. So some folks said, we really don't need to use addresses there at all, do we? If you took your networking topology that we've been working with, that's where we would assign /30s. Now the /29s would still be on all the host addressing, but /30s would be on all the point-to-point links. Remember here that if we're thinking about aggregation, there are two /30s inside a /29. Okay, so what does /30 really get us in terms of addressing efficiency? Well, if we had 8 point-to-point links, which we did, that consumes 64 possible addresses when using /29. So that's just the address space left to hosts. But 16 of those were the net IDs and the broadcasts. If we switch to /30, instead of using those 64 addresses, we're only using 32 now, and so we recover half of that space. So now all of a sudden we're back up to 87.5% efficiency. Now that's a little bit better, but can we do even better than that? What if we use /31? Now I gotta give a shout out to Ken here, one of your classmates. He beat me to this, so he mentioned this in class before I could get it out here in the video. But here's what he was talking. If you follow the same thinking, right? And we do a /30, and we know that's 2 host addresses and a subnet ID and a broadcast ID. When you go to /31, it only has 2 addresses on that particular subnet. And so here's the way that it works. RFC 3021 says, if the links are everywhere, right? And you say, well, what's the big deal about conserving just 2 more addresses? Well, the example that they give in the RFC is that if there are 500 point-to-point links, you just saved 1,000 addresses, which is equivalent to 4 Class C. So it actually becomes a substantial amount of savings. So the idea here is that, okay, so when you're doing a /31, you only have the net ID and the broadcast address on that particular subnet. And what that means is that the routers must be assigned those 2 particular addresses. It's crazy, I know, it's weird, but that's the way that it works. So when you're doing /31s, and if you have a router that's capable of doing /31s, when you go to do it, a lot of times you get a warning that says, be careful, these got to be only used on point-to-point links. So those 2 addresses now are going to be interpreted as host addresses. And what this does now is it recovers, in our case, some of those addressing, and so now our efficiency goes up to 93.8. But for your advanced networking people out there, you might say, well, wait a minute. Normally we have that .255 or whatever it is as a broadcast address, right? All ones in the host portion is going to be broadcast traffic at that particular subnet. And so the answer here is that because we're taking that broadcast address and now we're going to assign it to a router, then any broadcast that's necessary has to use the limited broadcast. And from outside, so if you're going to broadcast into the network, well, it's kind of lost. But this is actually not really a big deal because there's no host to answer it anyway. At this point, routing protocols, which was another concern, whether or not they'd be affected by this, most of the routing protocols had switched to classless, multicast, or unicast addressing, so it didn't really have a big effect on routing protocols either. The weird part, if you're actually capturing traffic or you've got some kind of monitoring going on, that you would actually see traffic now sourced from a network ID or a broadcast address, which is not something we're used to seeing. Okay, so we're done, right? We're okay? Well, we still have to be clever about how we assign the addresses. Remember that before when we said, great, we can aggregate 8 /29s together into a /26 and just say, oh, those 8 are that way or those 8 are that way. We find out that the downstream routers can actually do some aggregation too. And so we still want to be clever about how we assign the address space. If we remember that on one side of R3 in our topology, we've got 9 networks. So we have 9 networks that way and 9 networks that way. 5 of them have hosts, so we might use /29s there. But 4 of them are point-to-point, so we might get away with a /30 or a 31 there. But then how do we assign those? We still want to obey those rules. Are there places where we can aggregate? And so in this example here, what I've picked is that low subnet in the range. So I've said the 200.150.100.0 network /29 is 0 to 7. And that's a /29. But if it's 2/30s, then the address space would be 0 to 3 and 4 to 7. Both the same size, both 4 addresses. But if we use /31s, then we all of a sudden have 4 of those networks in there. 0 to 1, 2 to 3, 4 to 5, and 6 to 7. So we could be clever about how we assign networks downstream and maybe figure out ways to even aggregate /31s together so that we don't have multiple routing table entries. All right, so if your head is spinning right now and you want to go through an example, let's go ahead and do it. So let's see how this works. Here we've got the 200.150.100.6/31. And that's the .6 and .7 both broken out into binary. Okay? Underneath that, I've split out the /31 mask, what it would actually look like. And when you do the ANDing process on that, you wind up finding out that they're both on the .6 network. Really weird, but that's what they are. And so this network has only 2 network addresses. So it works in the exact same way that we're used to seeing when we deal with subnetting or supernetting. By the way, this little graphic of the AND gate I thought was nice to remember the process that we're going through. And we're used to saying in networking, oh, anything ANDed with a 0. But another way to think of that, of course, is that it's a product. So when you multiply them together, anything multiplied with a 0 gives you a 0. So the only time that an AND gate gives you a pair of 1s or a 1 on the output is if you have a pair of 1s on the input. Everybody good? We have to be done now, right? Well, what if we didn't use addresses from our network at all? This might be yet one more way to recover some address space. So in some organizations, what we see is that on all these point-to-point links where we don't need hosts, particularly when we don't want to expose our routed interfaces or put them on the production network, then we might actually use private addressing. So let's think about this for a sec. If we assume that all of our hosts have public-facing IP addresses, there's no reason to have our routers doing that. Remember, routing is just numbers. You can use any network numbers that you want on your point-to-point links as long as the routing works. So you can say, I've got directly connected 10 networks and that I can get to the 200.150.100/whatever or .whatever/29 subnet via one of my 10 NAT interfaces. There's no reason to say that you couldn't do that. So it's just a numbers game. So you can use whatever addressing you want. The routing just has to work. But again, you'd still want to be clever in how you aggregate your host address space together. So we use private addressing all the time. We use it for routing protocols. Static routes have no problem with them. And of course, even loopback addresses, which are our management interfaces a lot of times, we use private address. And in that case, you'd recover all of the lost space and you can use every bit of it for your public-facing IP address. Okay, so this was just one set of examples on how to do this. There are a couple ways to do that. We talked through some that I didn't actually show you. So there are a couple ways to do it. The thing to remember is that even if it aggregates on paper, you still got to look at the topology and assign them to router interfaces in a way that the router can actually aggregate them together. So they've got to be, on the same topological lines. That's the key. We've got to watch out for lots and lots of things. So if you take a look at RFC 4272, it's actually BGP4 vulnerabilities, but in that RFC it talks about a lot of these things. Routing black holes and congestion can be caused by routers that are accumulating too many routes or too many pathways. Starvation is when a network cannot route to a particular node. And then also we have loops and lost segments due to aggregation. Now, one of the places that we see this a lot, and it's an example that we did in a previous video, is that when you're aggregating routes together, but you don't aggregate the entire address space, you leave out a chunk. And so what ends up happening is that not only can traffic not get to that particular space, then the router that is missing the chunk forwards the traffic back the other way to its default gateway, resulting in a routing loop. So that's very bad. A cut is a portion of the network that believes that it doesn't have a route to the destination, even though there's some physical connection. And that's a routing problem that you've created because of the way either that you've assigned your routes or the way that you've done your addressing or something like that. So here's what I tell a lot of folks to do. When you're building your networks and when you're designing things on paper, go ahead and put your pencil on the paper. And, at this point, hopefully you've been able to figure out how to assign IP addresses on paper to routers or in a topology diagram, and then you can build the routing tables. Put your pencil on that paper and follow it from source to destination and be able to get back. And if you can follow that and process the routing tables, and your routing tables get you to the destination, and then your routing tables can get you back, you probably have a pretty good design. So that's really the key. Wash, rinse, repeat. Try that a couple of times from different sources and different destinations. So let's take one last look. So what I decided to do as we close out this particular video is say, well, I'll take a portion of the network. So what I did is on R3, I said, let's go ahead and assign a particular address. So there's a couple of things that I want you to notice here. One is that I have /29s for all my host addressing space because that was the size that we sort of decided for the hosts. Where that I assign them though, they can be aggregated together. So the 0 and 8 can be aggregated together. The 16 and the 24 can be aggregated together. So that means that R4's routing table can be simplified. In addition, all of the address space that I use on those 8 networks can in some way be aggregated together. Now they're not /29, so we got to think about that for a sec. 0 to 8, 16 to 24, but actually 0 to 24, those 4 networks can actually be aggregated together. And in addition, the .32 up there is the continuous space or the next portion of the address space. So I wanted to keep using that address space. Because what I also decided to do was make all my /31s. Remember that we said 4 /31s can fit into that address space. What I decided to do was that all 4 of my /31s will come out of the next chunk of address space. So the .40, the .42, the .44, and the .46, all /31s, but all in continuous address space. So if you take a look at my routing statements here, I've given that R3 has actually got the IP address of .40. So that means that the R4 interface is just .41. So now I've got the 10.150.100.0 /27 connected via .41. So that's all 4 of those host addresses down at the bottom. And then I said, well, .42, the .42 /31 network also connected via .41, and then 44 and 46 are aggregated together into that one mask ending in .252. Now, as I look at this, it looks like I forgot to add the .32. So you guys will just have to forgive me on that one. We've got the /31s, we've got the address for the router itself, which is .40/32, and then we've got the /27, /31, and /30 for the other static routes. And again, we forgot the .32, which would have added another /29. Well, there you have it. There's the actual commands and actual routing table. Thanks for watching. Make sure you keep an eye on those routes, and may your packets always reach their destinations.